welcome everybody to week 2 of the physical science course online. And what I'm going to do here is I'm going to go ahead and share my screen. And what we're going to look at is this PhET simulation called the Moving Man. So this is put together by the team at the University of Colorado Boulder. These nice interactive physics simulations. So what this one is, you can see the web address up here to get there if you want to do this yourself. In fact, why don't I just put it in the chat here. So I'll just paste it over here into the chat. So anybody who watches it afterwards, you're welcome to, use Teams and use the chat and just do all the stuff that I'm doing, or do your own version of all the stuff that I'm doing. Okay, so let's share the screen again. And basically, if you hit the little play button, it gives you a couple options for how to run it. I'm just going to use this version. As soon as it loads, it basically is a little simulation that will load, that will run in your browser. So it should work fine with whatever internet browser you have. All right, so there's two versions. There's the introduction version, there's the chart version. Chart version means there's going to be a graph. Introduction version just means the guy's gonna walk as per whatever I do here. So like I can click on this guy and I can move him to somewhere and it will move his position to there. And then if he's just standing there, then velocity is 0 and acceleration is 0. So, and I guess you can also move the sliders for these. So what if we reset everything here? What if we sort of move the guy to a particular location? Let's say that we start him off over here at this little tree. So the tree is at position -8 meters. So here we are, he's at the tree. And here's the house. And maybe I say I want to set this up in such a way that the guy gets from the tree to the house in, let's say, 4 seconds. Okay. So in some sense, this is like challenge question. How do you get from the tree to the house in 4 seconds? So let me pull open my little workspace. This is the problem with having too many classes that I teach, is I also have too many of these folders that I have to dig through to find anything. Here we go. Pardon the mistitling and everything. I just needed a PowerPoint worksheet here. So let's get this thing back up. I'm going from here, this is at -8, to here, +8 in 4 seconds. Okay, so if I go to my worksheet, so we have our delta x. Our delta x is our final minus our initial. This is what's called displacement. And very sorry, by the way, for those of you who watch this, that when I say something and then when I write it, they're not going to be totally synced. So it is what it is. You've been forewarned. Okay, this is called displacement. And in this case, the displacement delta x is from +8 meters, +8.0 meters. This is the house. And it's from -8.0 meters, the tree. So we can label these house and tree. So again, where did I get those numbers from? He's starting here. Initially, he's here, -8. This is where the tree is. he has to end here at the house at +8. Okay, so my displacement, therefore, 8 minus -8 is the same as 8 plus 8. This is 16, and with significant figures, 16.0 meters. All right, so that's my displacement. Now, recall that the question was, what speed, and parenthetically, what constant, and really it's a velocity because there's a direction as well. And this is what is needed to make the man walk from tree to house, walk or run, in 4 seconds. So you'll recall that velocity is defined as rate change of position, or in other words, the displacement per unit time, delta x over delta t. This is velocity. It follows that in this case, v is equal to positive 16.0 meters. We found the delta x up here, in other words, and this really is a displacement vector. So we can put the little vector sign over it because of the plus and minus signs. 16, and then in the question it says in 4 seconds, so divided by 4.0 seconds. So this should be 4 meters per second. Okay, now we can test it out. So of course I have to pull the right window up, but we can test it out by coming over here and setting this velocity to 4 meters per second. I guess he's going to be kind of running. This is kind of close to 10 miles an hour. So this is actually more running than walking. So when I hit play, this timer will start. He'll start moving with this velocity. I've made the acceleration 0. That means there will be no change in velocity. And we just want to see, when does he arrive here at the house? Does he arrive in 4 seconds like we predicted? So ready, go. And stop. Oh, right on the dot, 4 seconds, and he's right at the house. So our calculation agrees with this simulation. Okay. Now let's say that we want him to go back to the tree. And this time, in order to make him go back, we have to make this number negative. So let's make this negative, and let's make it 2 meters per second. So he's just gonna walk back, a brisk walk, but he's gonna just walk back to the tree. Okay. So question, what do you think his average velocity for this entire trip is going to be? Okay. What do you think his average velocity for the entire trip is going to be? So I'm going to write this over here. And if you're watching this from after I've sort of recorded it and everything, this is a good time for you to try to calculate this number on your own and then compare it to the number that I get. Okay. So let's just make ourselves a blank thing. So now the man walks back all the way back to the tree, and he's going to do this in, at a velocity of negative 2.0 meters per second. Okay, therefore we want to know what is his average velocity for this motion. All right. Well, recall that average velocity is the same thing as total displacement divided by total time. Now, we don't know what the total time is, but we actually know what the total displacement is, because this is the same as where he finishes minus where he starts. And in both cases, he starts and finishes at the tree. So this is negative 8.0 meters minus negative 8.0 meters. And then divided by some amount of time. We know it's not 0 because he's already taken 4 seconds to get from the tree to the house. So some non-zero amount of time. And the reason why it's important that it's a non-zero amount of time is because this difference right here is actually zero. He's started and stopped at the same place, so his displacement is zero. And therefore his average velocity is 0 meters per second. Now there's a related question. What about his average speed? Okay, what about his average speed? So to do that, the average speed, V, is distance traveled. Essentially think of this as like an odometer distance. It always goes up, divided by time. Now the distance traveled, he went 16 meters to get to the house, and then he came 16 meters back. So this is 32 meters divided by whatever the time is. Now, what's the time that's going to be required? Well, we have 4 seconds to get from tree to house. And then to get from house back to tree, it's a similar calculation to what we did on the previous problem. So delta T from house back to tree is this distance, which we again know is 16 meters, divided by the speed, which was 2.0 meters per second. So that is 8 seconds. Okay, so we have 8 seconds right here. So that's 32 meters divided by 12 seconds. Okay, and so that ends up being 2 2/3. So call it 2 point, with two significant figures, maybe 2.7 meters per second. That's his average speed. Now notice that this is not the speed that you would get if you said he went 4 meters per second this way, he came back 2 meters per second, 2 plus 4 is 6, divided by 2 is 3. The average of the numbers 2 and 4 is 3. That's not going to be his average speed though. Average speed is actually weighted. Whoops. Specifically, it's weighted by the amount of time that you spend at each speed. He spent more time at the slower speed than he did at the faster speed. So his average speed is going to tend to be closer to the lower of the two speeds. Okay, so now we don't have a way with the simulation here to get his average, his average speed. But we can check and see if we have to add another 8 seconds in order for him to get from this house back to this tree. So let's see if that's true. So we should be able to hit play, and this should go from 4 up to 12 when he gets around to this tree. Okay, so let's go play. Waiting for him to get to the tree before we hit stop. There we are. So here's 12 seconds. He's just basically passing the tree at 12 seconds. He was maybe not quite entirely all the way to the house when we started, but he was close enough. So the simulation seems to agree with our math here, that it should take him about 8 more seconds to get back to the tree from the house. So, all right, there's 2 questions. Let's do one last question, a little bit harder of a question that we'll use this running guy for. So let's reset everything. This is silly. Let's put him at 8 and, or excuse me, at -8. So last challenge here. Let's say that he is initially resting by the tree and he decides to start moving towards the house, and he increases his speed steadily as he moves from the tree to the house. Okay. Let's say that he is going to do that at a rate of acceleration of, let's say, a half meter per second. So 0.5 meters per second squared. All right, so notice he's going to move in the direction of the green arrow, that is towards the house. We want to know how much time is it going to take for him to get from the tree to the house in this case. So let's come over to here and let's write our question. So we want to know, given this steady acceleration of 0.5 meters per second squared, how much time he's going to take to get to the house and how fast he's going to be traveling when he gets there. Okay. So basically for this part, let's call it A and B. So part A and part B. For part A, we can use that distance, delta x, is equal to 1/2 of the acceleration times the time squared plus the initial speed times time. Now he's initially at rest, so this second term is 0. It follows that the time needed is going to be multiply both sides by 2, divide both sides by a. So the time squared is going to be 2 delta x over a. So to get the time, I have to take a square root. Okay, so this is therefore square root of 2 times 16 meters divided by 0.5 meters per second squared. So this should come out to 8.0 seconds at this acceleration rate. So now we want to know how fast he's going to be traveling when he gets to the tree. So his final speed is his initial speed. Oops, I'm using a 0 for that. V0 plus acceleration times time. So again, that's 0 meters per second. This initial speed is 0 plus 0.5 meters per second squared times 8.0 seconds. So the final speed, according to this, should be 4 meters per second. So you should be arriving at the house at a time of 8 seconds with a speed of 4 meters per second. So let's test that one out. Okay, ready? We'll hit play and then I'll try to stop it when he gets to the house. Ready, go. So he's picking up some speed, picking up some speed, picking up some speed, stop. Okay, so I got just a little past the house, but here we are, 8 seconds, 8.1 meters, so just a little too far. Speed 4.0 meters per second. So within my reaction time, these two numbers both agree with the numbers we got here, and and position being just a little over those 8 meters. Okay, so it worked. Cool. So any of you who are watching this sort of after the fact can go to the website that I've put here and play with the simulation yourself and make up your own games if you'd like with it, or test it out on your own and see, is there any hidden tricks that I'm using? There aren't any. I'm just doing basic physics. I'm using the equations you guys have in class. In principle, you could also try to use this to double check the work on some of your homework problems. If you're going through homework problems that happen to have a position, velocity, acceleration, that kind of stuff. So long, of course, as you are keeping yourself between about minus 10 meters and 10 meters. Now I think actually you can take away the 2 bricks and you can make this larger. Like, what if we want him to be at 0 meters and initially not moving, and he has this kind of acceleration? We want to know, when does he get to 12 um, meters, something like that. So you can push play. Whoops. I guess it decided that it didn't like my acceleration. So reset all. Yes. Take these off. Make this 0.5. So when does he get to 12 meters? So basically just watch this number till it hits 12 and then we hit pause. So 7, 8, 9, 10. That's 11.96. That's pretty close to 12. This happened in 6.9 seconds. So you can use this if you want to play with some of your homework problems. Not all of them will work for you, but quite a few of them will work, at least in chapter 2. So that's all that I'm going to do in today's little session. So anybody who decides to watch this after the fact is welcome to try any of this out on your own, and I guess enjoy. So let's quit recording and let me say farewell to everybody.